All right. Today we are going to talk about practical sources, and then we are going to talk about the maximum power transfer theorem. So a practical source is a source that contains both an ideal source as well as some resistance that helps model the behavior of a real current or voltage source. So over here on the left, we're going to have a practical voltage source that contains an ideal voltage source Vs and a resistance Rs. And over here on the right, we're going to have a practical current source that's going to contain an ideal current source Is in parallel with a resistance Rs. So can anybody tell me what the resistance does for our practical voltage source? Right, hearing a lot of nothing, that's okay. So if I had just an ideal voltage source, how much current could that voltage source supply? What? So let me rephrase my question. Let's say that I have some voltage source like so, connected in parallel to a short circuit. What would my short circuit current have to be in this situation? Ooh. So if the short circuit current were zero, that would imply that the wire does not exist. Infinity, absolutely right. So if we had an ideal voltage source and we shorted out its terminals, our current would need to be literally infinitely large, yes. Every current voltage source that we've dealt with to this point has been an ideal source, meaning that the voltage that it is supplying or the current that it is supplying is completely, let me think of how to put this. So for this particular case, this voltage Vs is going to be between these two terminals, full stop. That's what an ideal source is. It supplies a certain amount of voltage or current, regardless of what things are connected to it, okay? So for this voltage source, let's say it was 5 volts, that means there's a potential difference of 5 volts between those two nodes. Now, I've intentionally broken things here by putting things in this voltage source in parallel with a short circuit, which we know the voltage drop across the short circuit should effectively be infinity, which is telling us that our current is going to be infinitely large in order to try to make this thing work. Now, can a real current source ever supply a real voltage source ever supply an infinite amount of current? Absolutely not, okay? So the purpose of this resistor here, Rs, is to limit the amount of current that flows out of the voltage source down to some real value. Typically speaking, for a well-designed voltage source, which are not the DC power supplies that we have in this room, by the way. But for a well-designed voltage source, the source resistance is usually going to be on the order of milliohms. It's going to be very, very small. For most batteries and stuff like that that you can buy, it's usually in the tens to hundreds of milliohms range. For the voltage sources that are around the perimeter of the room, it's in the 20 to 100 ohm range, and we'll see literally that when we learn about Thevenin equivalent circuits and test things when we get back from the break. So the purpose of this resistance RS for our practical voltage source is specifically to limit the amount of current that can be supplied by that ideal voltage source. For our practical current source, it's the opposite thing, right? So if I have a current source IS like so, connected effectively in parallel to an open circuit, I would see that my open circuit voltage would have to be infinitely large in this case to account for the fact that my current is flowing through something that has a resistance of infinity, effectively. And so the role of the source resistance RS here is to limit the voltage drop that can occur across a practical voltage source. Excuse me, practical current source, goodness. All right. So practical voltage source is nothing more than a voltage source like we've seen in series with a resistance. A practical current source is nothing more than a current source like we've seen in parallel with some resistance. Now, under very certain conditions, these two circuits, our practical voltage source and our practical current source, are electrically equivalent to each other, which means anywhere that we have a practical voltage source, we could replace it with a practical current source and vice versa. So let's figure out what those conditions for electrical equivalence are. And to do that, we probably need to review very briefly the concept of electrical equivalence, because it's something that we've been using, but I don't know if it's something that I've explicitly said to this point, okay? So let's look at something I know for a fact that we've done. Let's say that I have some voltage source Vs connected to a network containing a couple of resistors. Here's my resistor R1. Here's my resistor R2. I'm going to define the voltage drop across this network to be VL and the current flowing through this network to be IL. The circuit over here to the right will be one that is electrically equivalent. So I have that same voltage source Vs. Here I'm going to have some equivalent resistance, Req. This will be defined as my voltage VL and my current IL. So looking back at our left-hand circuit here, what would VL be? Vs. What would IL be? All right, so Vs divided by R1 plus R2. Absolutely right. And so what power would be absorbed by our load in this case? Well, that would just be VL times IL, or Vs squared over R1 plus R2. For two circuits to be electrically equivalent, they need to have the same voltage drop across the load, or for two networks to be electrically equivalent, they need to have the same voltage drop across their terminals, they need to have the same current flowing into their terminals, and they need to absorb the exact same amount of power. So if we look over here on our right-hand circuit and we constrain this system such that VL is equal to VS, and IL here would be equal to VL over REQ, and PL would then be, sorry, IL should be VS over REQ, my apologies. VS squared over REQ. Under what conditions are these two circuits electrically equivalent to each other? When REQ is equal to R1 plus R2, which is simply the series combination of those resistors. So we've been dealing with electrical equivalence this entire time. Anytime we've been able to combine circuit elements, it's because we were dealing with electrically equivalent networks. We're just going to extend that to something that's a little bit more difficult, okay? So I'm going to draw over here on the left a practical voltage source. Connected to an arbitrary load resistance. And over here on the right, I'm going to have a practical current source connected to that same arbitrary load resistance. Here's VL, here's IL. So what would VL be for my practical voltage source representation here? How might we figure that out? Voltage division, absolutely right. So using voltage division, I could say that VL is going to be VS times RL over RS plus RL. What would my current IL be? So we could do it that way, but let's put it in terms of VS. So VS over RS plus RL. Let's look over here on the right-hand side. What would VL be? I think we can just use Ohm's law. Yeah, IS times the equivalent resistance, which would be RS RL over RS plus RL. We could find IL using current division, right? So that would be IS times 1 over RL divided by 1 over RS plus 1 over RL, which is the same thing as IS times RS over RS plus RL. So my question to you guys is, under what condition are these two voltages the same? So I have a fraction over here on the left-hand side of RL divided by RS plus RL. And I feel pretty strongly that I have a fraction on the right-hand side that is also RL over RS plus RL, which means that VS has to be equal to IS times RS for these things to be electrically equivalent. Now let's look at the current relationship. So on the left-hand side, I have IL is equal to VS divided by RS plus RL. On the right-hand side, I have IL is equal to IS times RS over RS plus RL. And once again, I can very easily see that I have a common fraction here, a factor of 1 over RS plus RL. And so I can see that for the currents to be electrically equivalent, VS has to be equal to IS times RS yet again. I didn't have enough space to put it on this page, but it should be fairly obvious that that would be the exact same condition that would make the power absorbed by our network electrically equivalent as well, since it's just going to be the product of those two things. Okay. So effectively, I can transform between a practical voltage source representation and a practical current source representation if I hold that VS is equal to IS times RS. So we have now stumbled onto what's called a source transformation. So if I have following network where I have a resistance in series with a voltage source, I'm going to call this RS, and I'm going to call this VS. We can convert this into the following network. My stylus will write. So this current will be VS divided by RS, just using our relationship from earlier. I want you to note that the positive polarity terminal of the voltage source tells us what direction our current should flow in our practical current source representation. So if our positive polarity terminal is on top, our current is flowing up. Positive polarity terminal of the voltage source is on bottom, the current's flowing down. Positive polarity terminal of the voltage source is on the right, the current's flowing to the right, etc. Okay. We can also go the other way around. So if we had a practical current source representation where we had some current IS in parallel with some resistance RS, this could be converted into a practical voltage source where we would have RS in series with a voltage source, and the value of this voltage source would be IS times RS. And once again, the same rules apply. If our current is flowing up, that means the positive polarity terminal of our voltage source is on top. The current's flowing down, the positive polarity terminal of our voltage source is on bottom, and so on and so forth. So anytime that we see a practical voltage source, we can replace it with a practical current source if it will make our analysis easier. Anytime we see a practical current source, we can replace it with a practical voltage source if it will make our analysis easier. So this is just another trick to add to our toolbox in order to make analyzing circuits a little bit better. So let's work an example here. So let's say that we have the following circuit. Let's say that our goal was to solve for the current IX in this circuit. So let's also say, just for the sake of argument, that this was a test question or something like that, so that we couldn't, we were constrained to a 3-equation, 3 unknown system if we wanted to solve for this thing. Okay. I'm trying to give us a reason not to just use node-ware mesh. How many meshes does this circuit have? Yep, 4 meshes, okay. How many nodes? 5, which is beyond the capability of most of our calculators to solve unless you happen to buy the Casio 991, then you could do it with node-ware mesh. But not all of you bought that one. What I would like to illustrate to you guys is that we could take this complicated looking circuit and within a few source transformations, actually break it down into a single loop circuit that we could have solved on the 2nd or 3rd day of class. Okay. So the first thing I'm going to do is I'm going to identify my practical current sources. So I have a practical current source over here to the left that I'm going to box in red, like so. I have a practical current source over here to the right. I'll box in blue. And I have a practical current source up here on top that I'll box in purple. So even though it has a dependent source, it's still a practical current source because it's in parallel with a resistor. So if I perform source transformations, so let's start with the network on the left. What would 3 amps in parallel with 7 ohms transform into? So 3 times 7 is 21. So 21 volts, positive polarity on top. I missed the 1. In series with a 7 ohm resistor. That was my network in red. What about my practical current source in the top middle in purple? What's that going to transform into? Eight IX in series with 4 ohms. Is the positive polarity terminal of the voltage source going to be on the left or the right? On the right, absolutely correct. So let's go ahead and drop that guy in. And then lastly, we have my practical current source on the right. 6 amps in parallel with 1 ohm. What's that going to look like? 6 volts in series with 1 ohm. Positive polarity of terminal of the voltage will be on top. Oops, not what I wanted to have happen. There's 1 ohm. Volts. And now I'm just going to connect everything else. So between this terminal here and this terminal here, I just had a short circuit. Between this terminal here and this terminal here, I had a 7 ohm resistor. And between here, I had a 5 ohm resistor through which my current IX was flowing. And like I said, now I have a single loop circuit that we literally could have analyzed on the second or third day of class. So we took something that would have taken pretty large nodal or mesh relationships, 4 equation, 4 unknown at a minimum kind of thing, plus a controlling variable, so that would have added a 5th equation and all that kind of stuff. And we got it down to a single loop circuit just by using source transformations. Yes, Brand. It does not. So because they are in series, it does not matter if you put the resistor on top or bottom, to the left, to the right, whatever. The resistor can be anywhere as long as it's in series with the voltage source, and the voltage source is the polarity, or excuse me, the polarity of the voltage source is correct based on the direction of current flow. You're good to go. So we could have just as easily put this 7 ohm resistance down here, or move the 4 ohm resistor and the 8ix source. We could have swapped them around. We could have put the 1 ohm resistor down here. It doesn't matter, as long as it's in series with the voltage source, we're good to go. Same thing when we're going from a practical voltage source to a practical current source. We could put the resistor on the left or the right. It doesn't matter. They're in parallel. All right, so at this point, we could solve this very easily. That's boring, so I'm not going to do that. Okay. Instead, now let's talk about what's called the maximum power transfer theorem. Let's say we're going to derive this using a practical voltage source, but we could do it just as easily using a practical current source. Let's say that I have a circuit like so, where I have been able to represent some larger part of a circuit by a practical voltage source. And my practical voltage source is connected to some load resistance RL. Once again, we're going to define the voltage drop across our load resistance as VL, and the current flowing through our load resistance as IL. So, how did we solve for VL earlier? Voltage division, okay. So VS times RL over RS plus RL. Our current IL we got just by doing Ohm's law. So that's going to be VS divided by RS plus RL. And now let's explicitly look at the power, since we're trying to figure out how to maximize power quantity. So I'm going to multiply VL times IL. And that's going to look like VS squared times RL divided by RS plus RL squared. So if I were to plot the power absorbed by my load resistor, it might look something like this. So this is going to be the power as a function of the value of RL. And this is going to be RL on this axis. So way over here, where our power absorbed is 0, is when our load resistance is effectively a short circuit, right? So if our load resistance had a resistance value of 0 ohms, we know that it should not be absorbing any power whatsoever, because the voltage drop across it would be 0, right? So 0 squared divided by 0 is going to give us 0. Way over here on the right-hand side, where we're once again absorbing no power, corresponds to a load resistance of infinity. So effectively, if there's no current able to flow through our load, we shouldn't absorb any power either. And then everywhere in between those points is every possible resistor value that could ever happen, right? Everything from 0 all the way out to infinity. We can see very explicitly that there is one particular point where maximum power is drawn by our load resistance. So our goal here over the next few minutes is to figure out A, what that value of RL is that causes maximum power transfer to occur, and then B, once we figure that out, determine what the maximum average power will be. So I have this function. How do I determine the maximum value of a function? Take the derivative of the function and set it equal to 0. Absolutely right. So we are going to take the derivative of our power function with respect to load resistance and set that equal to 0. Okay? So the derivative of PL as a function of RL with respect to RL is going to be the derivative of VS squared times RL over RS plus RL quantity squared. Now, to me, this looks like a great place to apply the quotient rule in calculus, right? So if I have the derivative of f of x over g of x, please remind me if I'm doing this incorrectly because it's been a hot minute, but I believe this is f of x times the derivative of g of x minus g of x times the derivative of f of x all over g of x squared. So it's prime like that. Okay, like I said, it's been a minute. All right, so we'll see if this shakes out correctly. So my f of x in this case is going to be, well, obviously my numerator, which is just VS squared times RL. And my g of x is the quantity RS plus RL squared. Okay. So let's see here. So what's the derivative of VS squared RL with respect to RL? VS squared. So we'll have VS squared times RS plus RL squared minus, all right, so what's the derivative of RS plus RL quantity squared? Twice RS plus RL times VS squared RL divided by RS plus RL, quantity to the fourth power, because we're squaring the squared. And this must be 0. And in order for this to be 0, our numerator just needs to be 0, right? So let's play around with some things here. So we have VS squared times RS plus RL squared, which is going to look like RS squared plus twice RS RL plus RL squared minus 2 VS squared. Then I'm going to have an RS times RL, and then an RL times RL. Did I do my algebra correctly? Molly, did I screw anything up? Okay, I don't think so either, but I can get bad at this. All right, so the first thing that I can notice is that I have a common factor of VS squared on both sides. So this VS squared and this VS squared effectively are going to go away because I can just divide both sides by VS squared, and 0 over VS squared is still 0. That all works out okay. I have a positive 2 RS RL, and then I have a negative 2 RS RL. That's going to go away. And then I have, let's see, so I have RS squared plus RL squared minus 2 RL squared. What the hell happened? So to me, that's going to look like RS squared minus RL squared is equal to 0, which implies that maximum power transfer occurs when RL is equal to RS. So I'm going to update my graph here. So, and now let's take a moment to derive our equation for maximum power transfer, right? So our maximum power will occur when RL is equal to RS. So looking at our expression, we're going to have VS squared times RS, where I'm simply replacing RL with RS, divided by RS plus RS quantity squared. This is the same thing as VS squared RS over 2RS quantity squared, or VS squared RS over 4RS squared Or finally, 1/4 Vs squared over Rs. So this is our equation for maximum power transfer when we have a practical voltage source representation. This is going to be the exact same thing as 1/4 Is squared times Rs if we had a practical current source connected to an arbitrary load resistance. And I can get that either by deriving it fully or just saying, well, I need Vs to be equal to Is times Rs, and then that's how the math shapes out. All right. Let's work one of your in-class assignment problems. So this would be in-class assignment number 8, if memory serves me correctly. This first problem is fairly straightforward. It's simply just practicing the transformation. I'll let you guys do that. We're going to work on problem 2. So we're asked to calculate the maximum amount of power that can be delivered to a well-chosen load resistor RL. Just as a heads up, this is practically exactly how I phrase these maximum power transfer questions on the exam, which you'll see if you look at any of the practices. So we need to figure out what value RL will have, and then use that to calculate our maximum power transfer. So effectively, what I'm asking us to do is to convert everything to the left of that dashed red line into either a practical voltage source or a practical current source. So everything's going to combine down into either a practical voltage source or a practical current source. And once we get it at that point, we can just apply our equation for maximum power transfer. So how many practical sources do I currently have in this circuit? 2. I have one practical voltage source and one practical current source, right? My practical voltage source is this 27 microamps in parallel with 750 kiloohms. So I'm going to put a box around it. And then this 1.2 mega ohms in series with 15 volts is also a practical voltage source. So I'm going to put a blob around that, as it were. All right, so let's do a source transformation on the practical current source first. So 27 microamps, 27 times 10 to the minus 6 times 750 kiloohms, so 750 times 10 to the positive 3, comes out to be a voltage of 81/4, and I'm going to leave it in that fractional form. Right? So we would have plus minus 81/4 of a volt in series with 750 kiloohms in series with 3.5 mega ohms. Here we have 1.2 mega ohms series with 15 volts, excuse me. In series with 7 mega ohms. if that was in parallel with 7 mega ohms, in parallel with our load resistance RL. So before we bother about our source transformation on the practical voltage source, let's observe here that we can now combine the 750 kilo ohm resistor and the 3.5 mega ohm resistor, right? So that source transformation actually wound up putting two resistors in series, which weren't before. So it allows us to do a resistor combination, right? So 750 kilo ohms in series with 3.5 mega ohms is going to look like 4.25 mega ohms, right? 3.5 plus 0.75 is 4.25. So at present, I have a practical voltage source in parallel with another practical voltage source, which is an odd looking thing. However, if I do source transformations on both of those practical voltage sources, I will then have two practical current sources that are in parallel with each other, which will set me up such that I can do current source combinations and resistor combinations. Okay? So I'm going to combine, or excuse me, I'm going to transform this practical voltage source and this practical voltage source in the next step. So what's 81/4 of a volt in series with 4.25 mega ohms going to be? Some extraordinarily tiny current in parallel with 4.25 mega ohms. Direction of the current is going to be up. We'll sort out what that number is going to look like here in a moment. And then I'm going to have the 1.2 mega ohms multiplied, or excuse me, 15 volts divided by 1.2 mega ohms. So that's going to be a current source in the up direction. We'll sort out what number it has in a moment. In parallel with 1.2 mega ohms. This is in parallel 7. And then over here is our load resistance RL, like so. All right, so 81/4 divided by 4.25 times 10 to the 6th gives me 4.765-ish microamps. I'm going to store that as A in my calculator so that I don't have any rounding issues. 15 volts divided by 1.2 mega ohms looks like 12.5 microamps. And what can I do now to simplify this thing? So I have two current sources in parallel, and I have three resistors in parallel. So I'm just going to combine my current sources and combine my resistors, right? So my previous answer plus what I have stored in my calculator is A, gives me 17.265 microamps. Let's see, so 1 over 4.25 mega ohms plus 1/1.2 mega ohms plus 1/7 mega ohms. All of that to the -1 power. 714/865. So 0.825 and some change mega ohms in parallel with my load resistance RL. So what value of RL makes maximum power transfer occur? 0.825 mega ohms. So I'm just going to store that as C. And our maximum power is going to be 1/4 times that 17.265 microamps squared times that 0.825 mega ohms. So 1/4, 17.265 times 10 to the -6 squared times 0.825 times 10 to the +6. I get 61.479 microwatts. A little bit of rounding error, but pretty darn close. All right, so that's all I have for today. Just as a heads up, this is the last material that will be on exam 1 when we get back from the break. So we have 2 class meetings when we get back, Thevenin and Norton equivalent circuits 1 and Thevenin and Norton equivalent circuits 2. Those 2 lectures can be used on exam 1, but you are not going to be explicitly tested on them. So effectively you have the entire break and then 2 more class periods to synthesize everything that we've gone through to this point before you'll be tested on it the following Monday. If you have any questions, I'd be happy to answer them. If not, work on your in-class assignments, all that kind of good stuff.